You started to see that we are, in many cases, we can decompose maybe a seemingly cumbersome, complicated matrix into summations of easier to work with matrices, submatrices. And that is actually key in the analysis that we're going to go through now. Stability theorem. Here is the basic picture, big picture of what we're going to talk about in this landscape. Stability is something that's so fundamental for anything that we work with. We want it to be stable. We don't want to have catastrophic failures for control systems. But if you design not carefully enough, you can get stability issues. So I'm going to talk about the definition, usual definition, and then talk about for LTI systems, linear time invariant systems, how we can judge stability of the theorem. This is using the method of eigenvalue or pole locations, right? It connects to your ordinary differential equation course. And then we're going to talk about this concept of Lyapunov approach to stability, one milestone for modern control engineering. So we're going to talk about some mathematic tools. I will review some very powerful tools for these special matrices like skew symmetric matrices that we talked about, symmetric matrices that we're going to go through, etc. Then we're going to talk about continuous time case, Lyapunov theorem, and discrete time case, Lyapunov theorem. So let's start with some tools that we're going to use. First of all, we have been talking about vectors, matrices, over the last few lectures. We haven't talked about like how long, what's the length of a vector quite much yet. So there is this missing element of a metric, how we measure the size of a vector. And the norm is going to fill that blank. Norm, by the simplest common definition, you have seen this very commonly, right? So you can evaluate the length of a matrix, of a vector, by calculating the square root of the individual entries of the vector squared together. So this is very easy. A length in the two-dimensional case is like that. You calculate the length by calculating the two components squared addition together. Higher dimension, just add everything together. So more, this is called two-norm, Euclidean norm, the length. In the general setting, it is a metric in a vector space. That's going to assign you, it maps you from a vector, right, to a number. It gives you a single number about the length of the vector. For us, we're going to use just mostly this one definition, the two-norm, Euclidean norm of a vector. But there are many more norms. If you do optimization, you're going to experience one norm, three norm, p norm, infinite norm, etc. But we're not going to go through that. The stability condition that we're going to talk about are things like that. If, let's say, we have an inverted pendulum or pendulum that look like this, we want to be able to know like whether the system is going to stay where it is, stable, right? The concept of stable. Whether the system is going to stay in that state, initial state, if you release the system from that state. It's very important to talk about the concept of equilibrium state, equilibrium point. It talks about the concept that it is a special state condition. If you release the system from this equilibrium, let's say for this case, I have a system x dot equals any function of x and t. The equilibrium point, equilibrium state, is defined such that if you start at this xe equilibrium, then your derivative is going to be zero. You're not going to go anywhere. That's the definition. This has to be satisfied for all the time in the future. You cannot, you stay here for a while and then you start moving, right? That's cheating. You have to be there all the time to be claimed as an equilibrium. So we talked about this. If you start there, you stay there. For inverted pendulum, this is an equilibrium. If you release from here, it stays there. And if you release here, then if there's no perturbations, you're going to also stay there. Right? So there are two equilibrium states. For us, most of the time, if you think about the system that we deal with, for us, let's say x dot equals to ax. X equal to 0 is obviously an equilibrium. If x is 0, then you don't go anywhere. Derivative is also going to be 0. So usually, we work on origin, 0, as the equilibrium point. Just to reiterate, if you have x equal to 8x, even if your a is changing, you are not time invariant, you are time varying, then x equal to 0 is always an equilibrium point. It may not be the only equilibrium point, because let's say if a equals to, so let's do it here, if a equal to 0, 1, 0, 0, then you can see that if you start at 1, 0, your x dot is also going to be a times x, right? Is also going to be 0. So you don't have to, 0 is not the only equilibrium. The equilibrium state can be non-zero state as well. All right, the whole concept of stability is about like whether you can stay around your equilibrium point. So let's talk about that. What do we mean by stay around an equilibrium point? We talked about metric. Here is the metric we're going to measure what do we mean by stay around an equilibrium point. Right? So it's useful to remind ourselves what is a continuous time function. By definition, continuous time function from the calculus is a function that satisfies this. If you, let's say you consider a point x0, you want to consider whether a function is continuous around this point. Then if this condition satisfies, then it's continuous, right? It's the epsilon delta language. If you look around this point in the local region, look around in the x, then if you if your x stays around, not too far away, then I can guarantee you that your output, your value of f of x, is also going to be staying around f of x0. So this is saying no matter, notice the language, no matter how small you choose, you want me to stay around my f of x0, I can always give you that result by choosing some epsilon in my input. So you can get very, very tiny around f of x0. I can make that happen for sure. And that is the definition of continuous time signal. Graphically, it's an unbroken curve, right? It doesn't have break, it doesn't have jump in this curve. It can be as complex as moving around like this, but as long as it doesn't have jumps, it's continuous time. All right, some simple functions that you can very quickly see the concept here. This gives us a concept of staying around a point. Now, in the concept of a control system, this is what it relates to. Lyapunov theory. This is a Russian mathematician and control pioneer. He actually invented this very early in the 18th century. But there's no internet, there's no telephone is not popular. And this powerful result remains unknown completely to United States and the West research community until approximately 60 years, 70 years later. And once it was discovered, this is a prime year for control theories. 1960s, 1970s, lots of results actually appeared. So this is one of them. Let's talk about the concept of staying around. The Lyapunov theorem says this. Let's say you have an equilibrium state. So in our case, it's something like this. It's equilibrium state. This is saying that this state, equilibrium state, is called stable in the sense of Lyapunov if for any epsilon and the initial time there exists a delta such that if you want my state to stay around this equilibrium, if let's say my equilibrium state is 0, if you want me to stay around this equilibrium, so give me any epsilon, I can make that happen. I can make my output to stay around this equilibrium state by giving you some delta and the initial condition. For that, and I'm going to guarantee you that for any future state t, the xt is also going to be stay inside, to be around this equilibrium state. So I give you a starting time, and then I can make sure that after this starting time, my state evolution is going to stay around this equilibrium. In the image, this is what it looks like. This is saying, let's say in a two-dimensional space, I consider this is the equilibrium state. And then the theorem is telling us, let's say, I can guarantee you that my future state evolutions is going to be staying around this ball, centered around this equilibrium state, right? This ball, you can give me any radius of the ball, let's say epsilon over here. I'm going to guarantee you, I can give you a starting point, and then all the future evolution of the state will be staying inside this ball. Question?
Yeah. Does delta always have to be smaller than epsilon?
Doesn't have to be. Yeah. The key concept is, I'll take it back. So if you think about the picture here, the logic is that all the future evolutions stays within this ball. So you have to start inside, right? Yeah. But that's the concept. It's, if you start around the equilibrium, it stays around it. It doesn't go crazy. That's the key point. If it goes blah, 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 goes crazy, then it's not stable, right? So that's the key concept. It stays around it. Now, this is a weak definition if you think about it. It only guarantees I don't go very far away, right? There is this concept of asymptotic stability, which is a stronger condition. It's called, the equilibrium state is asymptotically stable if you give me a ball, again, I can guarantee you that I start somewhere and then in the end I go to 0. I go to the origin. So I do this, then I move around, and in the end I go to 0. If that happens, if for t going to infinity the state goes to 0, then we call it asymptotically stable. There's a question?
So delta here is just like a scalar value function that takes in your epsilon and your t naught?
Right, so delta is just some initial, like, if you talk about this here, it's the initial length, like the radius of the initial condition. You start with some length of state vector within this delta value. Yeah, it may not be epsilon, it may be smaller or larger, but the end point is at the origin, then it's asymptotically stable. So this is stronger condition. Is not only stable in the sense of Lyapunov, right, but it in the end goes to origin. You start in some bounded region around the origin, and you go to zero, go to the origin in the end. That's asymptotic stability. All right? These concepts are very powerful. And then if you go back to what we have done for this system, then you will, let's see that these actually make sense. For these systems, let's take a look at x dot equal to a times x. So this concept of stable and asymptotically stable. Let's take a look at this one. If you give me an initial condition, x0, I know how it looks like. Is the evolution is going to be this. So for this system, it's very easy to tell. The solution of this EAT matrix, it contains, let's do this. For example, if it's distinct eigenvalues, so we know how it looks like. So it's going to contain a bunch of terms related to E lambda t or t times E lambda t, etc. Right? So if you have Jordan form, it has to t E lambda t term appears. If it's distinct, then it's only E lambda t. If lambda, let's say, is negative, if lambda is negative, -1, -2, or more general, the real part of lambda is less than 0. If your lambda is in this range, then E lambda t is going to be decreasing to 0, right? If this happens, then E lambda t goes to eventually 0. It's a decaying function. So if all the elements in the E lambda t matrix goes to 0, then you can see the entire thing, they must go to 0, right? So then I can be a little bit more specific. E lambda t, this one also will go to 0, because exponential function is some of the most powerful functions. No matter how you scale it by t squared, t to the power of 3, doesn't matter. E lambda t is going to go to 0. So all the individual elements in this matrix go to 0, then therefore xt goes to 0. Then in that sense, the system is stable around this equilibrium point 0. All right, let's take a quick break. We already talked about the concept, what it means for a linear system. So let's talk about more systematically the technique we can use. For continuous time, we talked about is the exponential functions. It's E lambda t or t E lambda t. For complex eigenvalues, you get E sigma t, etc. Right? So all these, if you can make sure that these are on the left half plane, even if it's complex, let's say right here, if sigma is less than 0, if sigma plus j omega is on the left half plane, then E sigma t is still going to decay to 0. So the response, these modes, these individual modes, is going to go to 0 if this condition satisfied. If the real part of lambda I should put it here. So if the real part of lambda is less than 0, then E lambda t or E sigma t is all going to 0. So that's how so this is strong stability, right? It goes to 0, so it's asymptotic stability. For discrete time systems, we have these modes coming up. So it's a to the power of k, and then in the modes, individual modes for A matrix, you have the eigenvalue to the power of k, or k times the eigenvalue to the power of k minus 1, or r to the power of k, etc. The definition of r is like the length, the radius of the vector, let's say, in the discrete case. So if your eigenvalue is here, then r is like the radius between the eigenvalue to origin. So you can see if it's real, then this is lambda, right? So in this case, for all these power functions, they will go to 0 if the magnitude, if the length is less than 1. So if it's 0.1, then you multiply 0.1 by itself multiple times, it gets smaller, smaller, smaller. The condition for the equilibrium point to be stable for discrete time case is the magnitude has to be less than 1. So two different conditions. For continuous time, this is the stability region. For discrete time systems, this is the stability region. So this is real part, this is imaginary part. These are the how you can judge stability based on where the eigenvalues are. Yes?
So if you have a discrete time representation of a continuous time system, could your discrete time representation appear stable even if your actual system is not, if it's within the unit circle but to the right of the imaginary axis?
Okay, so your classmate is asking, can I have a stable continuous time system but have an unstable discrete time system? What do you guys think? This is exactly using one technique we learned today. So if I have continuous time, what are my discrete time matrices? AD is E. Let's say I'm discretizing with sampling time delta t. So my discrete time A matrix is this one, right? If the eigenvalue of A are on the left half plane, what can we say about the eigenvalue of EAT? This is a question, right? We already talked about the spectral mapping. The eigenvalue of A, the eigenvalue of AD is the eigenvalue of lambda, is the exponential function of the eigenvalue of A times the sampling time. If my eigenvalue is less than 0, can I guarantee the magnitude of the discrete time eigenvalue is less than 1? No? Anyone else?
Isn't it the same thing though? Like if you break up lambda into A plus BI, then in the in the continuous time case, the real part of lambda is just going to be like your A, and then in a discrete time case, that's like that becomes like your radius.
Okay.
Right, like it. I don't know if that makes sense, but like. Sorry, I don't know. I don't know if that makes sense, but I can't like verbalize it.
Yeah. Let's do a simple case to start with. Let's talk about it's a real eigenvalue. Let's say lambda is real, so I don't need to worry about this extra complex modules. Let's say it's -1. Then we're going to be sure to have a discrete eigenvalue of this guy, which is what?
Which is a positive value, 1 upon e raised to.
Say that again?
E raised to minus 8 tau, or if I take the value of it, the norm of it, it's going to be a positive value, right?
Yeah, it's positive for sure. Yeah.
Exactly. So
But the question is whether it's less than 1 or larger than 1.
it will be less than 1, right? Because 1 upon e raised to.
Right? So exponential function looks like this.
Yes.
It starts at 1, and if it's negative, right? If it's negative, then it's going to be somewhere here. So this is less than 1.
Exactly.
If it's less than 2 or 3, then it's going to be somewhere here. So this is guaranteed. What about the more complex case? If it's, let's say, -1 plus 2j, then our eigenvalue in the discrete time case is e -1 plus 2j times t, delta t. So it equals e negative delta t times e 2 delta t times j. What is the magnitude here? Yeah. So Ola, this name is going to appear again. This one is e, I'm going to write it clearly, e negative delta t times exponential function of a complex number, which is, from the Euler equation, cosine 2 delta t plus j sine 2 delta t. And then I take the magnitude. Now what can you say now?
It is still less than 1 because magnitude of cos plus j sine is like 1, cos squared plus sine squared.
Right? So the magnitude of this one is square root of cosine square, blah, 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 plus sine square 2 times delta t, right? Sorry, my handwriting is a little bit sluggish here. But this is magnitude 1. So the whole thing is magnitude is e minus delta is less than 1. If you have a continuous time eigenvalues on the left half plane, your discrete time eigenvalue is also going to be inside the unit ball. So here is the thing that we need to be careful about. So the concept clear for this case. So it is very clear that when a system is stable or not. Right? So for a system to be stable, to be asymptotic stable, this is what we talked about. Real part of the eigenvalue less than 1 for all the eigenvalues, then is asymptotically stable. That's clear. This matrix, for notation purpose, this is called Routh-Hurwitz. Such a matrix is called Routh-Hurwitz. We're going to talk about the history of why it's Routh-Hurwitz later. But this is clear. Now, what we need to be careful about is the case where either we have eigenvalue that's larger than 0 or eigenvalue that's at the margins. When eigenvalue is less than or equal to, so equal to is bringing additional complexity here. Let's take a look at these two lines. It's unstable if any of the eigenvalue is larger than 0. If this happens, then the mode E lambda IT is going to go to infinity in the end, if there's eigenvalue larger than 1, larger than 0. So it is also unstable if, even if you have all the eigenvalues perfectly lying in the left half plane and some on the imaginary axis, but if you have repeated eigenvalues, say lambda m, on the imaginary axis with multiplicity m to be larger than the null space, the dimension of the null space, a minus lambda mi. So this is a statement. We will give you an example in a minute. So be careful about these marginally stable eigenvalues. It is stable, so this is unstable. It is stable if you have all these eigenvalues on the left half plane, and for these extra poles, extra eigenvalues on the imaginary axis, the dimension of the null space equals to the multiplicity of the eigenvalue m. Then it is also stable in the sense of Lyapunov. Let me give you an example, then you will see. So for this one, matrix A, 0, 0, 1, 0. So the eigenvalues are 0 and 0. Perfectly on the imaginary axis. The theorem tells us, in order to tell whether it's stable or not, check this condition. Check the dimension of the null space of A minus lambda I, and then compare it with the multiplicity of the eigenvalue. So for this one, the dimension of the A minus lambda I is the dimension, A is here, lambda is 0. So the dimension of the null space is 1, right? It has 1 independent solutions for the A minus lambda I. So if you do A minus lambda I times T, you want to compute an eigenvalue. The null space being 1 means that you can only find 1 linearly independent eigenvalue. You have to generate another eigenvector from the generalized eigenvector computation. So you have to have a Jordan form in J. 1 is less than 2. You have 2 repeated eigenvalues, but you need 1 generalized eigenvector. So in the similarity transform, you need a Jordan form, right? When a Jordan form appears for things like this, you can see what happens. If a Jordan form appears with 0, 0 here and 1 here, then the Jordan block is going to create a time sequence, a time function that looks like E times eigenvalue T, right? And then diagonal is, off diagonal is T times E 0T. This is the devil here. So the T element in the Jordan form is going to grow and grow and grow, and then goes unbounded. So when you have xt equal to EAT times some initial condition, then no matter how small your initial condition is, eventually EAT will have a component that goes to infinity, unbounded. Then it is unstable. All right. The basic idea, I reiterate, is actually to see whether Jordan form appears or not. If a Jordan form doesn't appear, then it's fine. If a Jordan form appears, then you're going to need to deal with things like this, right? When will a Jordan form do not appear? What kind of conditions for the null space A minus lambda I? Dimension of A, right? So if you can compute, if you solve this one, you have a null space, right? If it's 2, if you can get 2 independent eigenvalues, eigenvectors out of this, the null space is dimension 2. If that happens, then you won't have the Jordan block appearing. That is the key. As example, this is what we can take a look. It still has 2 eigenvalues at 0. So it's still multiplicity of this eigenvalue at 0 is 2. Now, if you compute the null space and see how many linearly independent eigenvectors you can pick from for A, you can see that the null space is null space of A minus 0, 0, so it's this. So you can pick two linearly independent T1 and T2. So T1 and T2, two eigenvectors associated to lambda equal to 0. That means you can form the T matrix directly from these two eigenvectors. So your Jordan block doesn't appear. Your similarity transform is going to be as easy as this. Nullity of A minus lambda I equals 2 equals to the multiplicity. That's the formula we check. From here, we can say that it is stable in the sense of Lyapunov because this condition holds. There's no eigenvalue, right? That's on the right half plane, so it doesn't go to infinity. You don't have E lambda t that goes to infinity. And then for this repeated eigenvalues, you don't have a Jordan block appearing. So it always stays bounded. Now you can check by verifying the solution. Xt equals, for this particular case, it equals EAT times x0, right? For A to be a zero matrix, this is identity times x0. So your system is going to stay at your initial condition. So it's stable in the sense of Lyapunov. Doesn't go unbounded. So this is something that's very useful to check, these two conditions. Especially for the case when there's eigenvalues on the imaginary axis. That's the only thing that we need to be careful about. Any questions for this part? Throughout the discussion so far, you may have noticed I never talked about I need to be able to compute the eigenvalues explicitly, right? This is the key. These tools that we talk about have the fundamental advantage. You don't need to compute where they are. You just need to know like whether they are positive or negative, whether they are on the left half plane or not. That's it. If you don't need to know explicitly the eigenvalues, then these tools we talk about, they're going to be super useful. You already experienced Routh's criteria. The full name is Routh-Hurwitz criteria. Hurwitz is the name that we mentioned earlier. If a matrix A, the eigenvalue are all on the left half plane, right? It's called Hurwitz, and the name comes actually from here. So because Routh, he discovered the tool that we use to take a look at the roots of a polynomial equation. And then Hurwitz, he independently developed the result by going from a linear algebra approach. He focused more on matrices instead of the polynomials. So that's why his name is used to describe this kind of matrices with eigenvalues on the left half plane. All this criteria doesn't require you to solve the roots specifically. You just need to take a look at a bunch of numbers and then you can get the result. All right. If you only need to know stability, then these are the approaches to go. This criteria, we can use it for asymptotic stability of the equilibrium point for this state space matrix x dot equal to ax. The key point here, the key observation here is this. When we translate from state space, when we transform from state space to transfer functions, these are the laws. So the transfer function, if you give me A, B, C, D matrices, I can know the transfer function directly. So stability of this transfer function can be obtained using Routh's criteria by looking at the denominator of this transfer function. Where does the denominator of the transfer function come from? It comes from precisely the determinant of Si minus A in doing this inverse. When you compute the inverse, you need to do the determinant of Si minus A and then the adjoint matrix. So this is the main observation. The eigenvalue of A are related to the poles of the transfer function by this fashion. So you can see here, this is precisely giving us the, if you do determinant of Si minus A equal to 0, this gives us eigenvalues of A. So eigenvalues of A are precisely the poles of the transfer function from this logic. Routh's array, quick summary. You have done this previously in the undergraduate control classes. So do this array if you're giving a polynomial coefficients an minus 1, all the way to a1 and a0. Then construct this array. Like do this first two rows of the array like this. Leading coefficient and then next coefficient and then go zigzag. So put all the coefficients in the first two rows like this, and then compute the remaining elements of this array by a formula. So be more specific. If you want to compute this one, the element right below the previous two rows are computed like this. So this element is computed by cross product B times C minus cross product A times D divided by the leading element in this row, C. For this one is similar. So is cross product C, so is take the leading column C times this one, X, the column next to the entry that you want to compute, C times X minus A times Y divided by the leading coefficient C. All right? The main conclusion is that you can tell whether these roots is going to be stable or not by looking at the sign change of this first column. All roots of the polynomial will be on the left half plane if and only if all elements in this first column they don't change signs. So we usually, for simplicity, we usually make sure that the sign of the leading coefficient is positive. Then you just need to see whether these are positive or not.
Sorry, did you explain what Q is?
Q? So Q, all these following rows are computed from the previous rows. So this is computed from these two elements. Yeah, and then do the same. So Q, this computed from these two rows. Yeah. All right, some practice just to refresh the memories. Let's say this is the polynomial 2s to the power of 4 plus s to the power of 3 plus 3s squared plus 5s plus 10. So do this. First coefficient here, second coefficient 1 here, and then go zigzag, and then 3, 5, 10. So the first element here is computed from, so this element is computed from these guys over here, is cross product 1 times 3 minus 2 times 5 divided by the leading coefficient 1. So it's this. So for this one is cross product for this one, 10 here, is 1 times 10 minus 2 times 0 divided by 1, so it's 10. Do the same for the following. This one is computed from these guys here. Negative 7 times 5 minus 1 times 10 divided by negative 7. So that's the result. So let's see how many sign changes. It changes from positive to negative, so it's unstable. And then at some point it changes from negative to positive again. So there are 2 sign changes in the first column. So it is unstable. If you want to know a little bit more, actually it tells you that there are 2 roots unstable in the transfer in the polynomial roots. Okay, there are like more special cases, like when some elements become 0, or sometimes the entire row becomes 0. How to handle that? We won't be focusing too much on these special cases. If you want to know more, there are references you can take a look, but that's not the focus for this class. All right. So these are continuous time stability conditions. The Routh criteria was developed for continuous time systems. Now let's think about if I have discrete time system. If I want to know like if the rules will be staying inside a unit ball, can I still use Routh array? Right? Let's take a look. For discrete time systems, any function that map from xk to xk plus 1, we have the similar definition of equilibrium point. So the definition here, so in continuous time is if you stop there, you don't move, right? In discrete time, it's the same. Is if your f function here, if you start at xe, it's going to give you the same. You are not going to move around. Your next state at time k plus 1 remains at the equilibrium point. Here, for this one, for the linear time invariant systems, this is what we mean. It means if xe, we start at xe, and then a times xc equals to xc, then it is a equilibrium point. All right? So let's take a look at something simple. So you can see immediately if xe is at origin, is 0, then this obviously holds. So 0 is always a equilibrium point for this system. Let's take a look at the conditions for the eigenvalues if we want the equilibrium to be stable. So let's take a look at the easiest case, asymptotic stability. So all these are concerned about this state transition matrix, right? So we need to think about what are the eigenvalue gonna behave for this a to the power of k matrix. If the eigenvalue of a are less than 1, we talked about the concept that all the eigenvalues in this matrix is going to be less than 1, right? So if lambda is less than 1, if lambda a is less than 1, then lambda, the eigenvalue of this matrix, if you talk about the magnitude, is going to be from our spectral mapping theorem. It's going to be lambda a to the power of k, and then you consider its magnitude. So if lambda a is less than 1, then this is going to go to 0 if k goes to infinity. So it's asymptotically stable if the eigenvalues are less than 1 for all eigenvalues of a. And then when that happens, the matrix A, if its eigenvalues are all less than 1 in magnitude, is called Skur instead of Hurwitz. All right. Things are relatively easy if you have eigenvalue that's larger than 1. If you have one eigenvalue that's larger than 1 in magnitude, then obviously you multiply it together, it's going to go to infinity, right? So if you have one eigenvalue larger than 1, then stability is violated. It's going to be unstable. What we need to be a little bit careful about is those eigenvalues that are on the boundary. So it's the eigenvalues on the unit circle. If I just take a look at the eigenvalue on the unit circle itself, lambda ak is going to be 1. It doesn't go to 0, right? So for these guys, lambda m to the power of k, it always equal to 1. It doesn't go to 0. It doesn't go crazy as well. Let's see. The extra care we need to take a look. If you have, let's say, repeated eigenvalues, repeated multiple times, and then has multiplicity of m, so you have m eigenvalues they're all on the unit circle. So lambda m, the magnitude is all 1. Let's see how we can tell whether it's stable or not. Key here is, again, if you have a matrix A, you do similarity transform. And you check the eigenvalue of J over here. You want to see what modes will come up in this computation. If you have Jordan block over here, let's say 2 by 2 case, Jordan block, let's say, is like that, then you can see the eigenvalues are on the unit circle. So it's going to have jk equal to what, based on our previous lectures? It's going to be lambda to the power of k, 1 to the power of k, 1 to the power of k. What is this element? Right? So that's the key. If you have any some kind of Jordan block appearing, then you're going to have some term that goes to infinity, that goes unbounded. Right? So this will go to infinity if k goes to infinity. So Jordan block will destroy your stability. And when will that Jordan block appear? It's again the same logic. If you have repeated eigenvalue, if you have 2 repeated eigenvalues, and you check how many linearly independent eigenvectors you can get. If the dimension of the null space of this matrix is less than the multiplicity, then you will be running out of eigenvalues. Jordan block will appear. So that's the logic. On the other hand, if the dimension of the null space is exactly m, the multiplicity, then you have sufficient eigenvectors. So Jordan block will not appear. All right, so that's how this table is derived. We talked about Routh array for continuous time systems. Now, this is going back about this mapping. It turns out Routh array can be applied to judge whether the roots of a polynomial is inside a unit circle or not. Out of the box, it tells you whether it's on the left half plane or not. But some simple modification can tell you whether it's inside a unit circle or not. All right? This is the technique called bilinear transformation. So there's a mapping here that's going to help us to map this S-plane, the left half side of the S-plane, into this unit disk. And this defined by this. Okay? So if you have, let's take a look at this one. Let's say if you have a eigenvector here. What I want to show you is that this is in the left half plane. And then by this bilinear transformation, it's going to be mapped to be inside here. So it's mapped like this. It's 1 plus s divided by 1 minus s. So if I say negative 1 is here and then 1 is here, it is 1 plus s is this vector here. S is here. It's s minus negative 1. Right? This vector is starting from minus 1 pointing to s. This is the numerator part. Denominator part is 1 minus s. So is this vector here. So the ratio between these is this one divided by this one. So what can we tell about the magnitude of z for this case? The length of the numerator is obviously less than the length of the denominator. So the magnitude of z is going to be inside the unit circle. So similarly, if you have a point on the right half plane, then you can see that the mapping is still s plus 1 is this one, and then 1 minus s is pointing to this direction. So for this one, 1 plus s divided by 1 minus s, obviously the length of the numerator is larger than the length of the denominator. So this one gets mapped outside of this unit circle, and this one goes to the inside of the unit circle.
To find the numerator and the denominator of the z,
Mm-hmm.
do you always draw vectors from negative 1 and 1? Is that what you did there?
Right. So this is, I try to illustrate the point that this maps indeed to this one. You don't have to draw it every time. What you do in the end is this. Once you understand the concept, the tool becomes, using the tool is just some technique in your notebook. So this is saying, if you want to know whether the roots of this polynomial are inside a unit circle or not, just apply this. Just apply this bilinear transformation. Let z to be 1 plus s over 1 minus s. Put it into here, and then consider the Routh array for this new polynomial. You see, after you substitute z with functions of s, this becomes a polynomial of s. So just apply Routh test to this polynomial, normal polynomial. Let's quickly, I'll talk about this result here. So if you have a discrete time, like transfer function, and you want to know the roots here, just do this bilinear transformation. And then translate it into a function of s, polynomial of s, and then apply Routh array as normal. So if you check all the elements in the first column are positive, then that means the roots of az are all in the unit circle. Take a look at the result. It's like a recipe. You just follow it and you get the result. Yeah. So I think what is more interesting is we do the computation to get the insights, right? We never do the computation to want to know a number. We always try to get some insights from the computation. So the interesting case is, let's say I have a design problem. Some of these numbers are not given to me, but are variables. Then becomes the design problem. I need to design a controller or something so that the polynomial, the roots are left out plane or in the unit circle, right? That's the thing. That's when it becomes interesting. All right. See you next time.